Okay, 6.1 is about linear systems and two variables. So quickly, a system means two or more equations working together. So we'll be adding another equation here in a minute. And linear, we know those are equations of straight lines, and we've looked at these before. And two variables just means an equation like this right here, where we have ax plus by equals c. That's the definition of a linear equation in two variables. Gets graphed on an xy axis. Or a lot of times what we do to draw the graph is convert it to this form, which is the slope-intercept form. And basically that just means solve for y. And then when you do that, you have the y-intercept here. It intercepts y at 5, and then you count your slope. In this case, a negative slope means the line's going downhill. And we can put the negative sign here or here, doesn't matter. Let me move it up here. So that would mean go down 2 to the right 3, 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 and you can draw your graph. We've done that before. What we're going to look at now are systems. In 6.1, it's going to be just systems of two linear equations and two unknowns. So let's add another equation here. Because right now, what I have, there is no one solution here. In other words, if I pick any number on the x-axis and I go up to the line, that's a solution. So 0, 5 is a solution. 3, 3 is a solution. Here, x equals 6, 7, whatever that happens. Here we go. We're at 6. I want to be on the grid here. X equals 6, y equals 1. 6, 1 is a solution. So there's infinite solutions because the line is infinitely long. However, that doesn't mean every point is a solution. For example, this point, that's not a solution because it's not on the line. That would be the point 6, 6, 3. So 6, 3 is not included. So any point on the line is a solution. All other points are not. Now we're going to introduce a second equation. Let me just make one up here. Let's do okay. And typically you'll see this right here. That just means this is a system. These two equations now are working together. So we're going to start by looking at different kinds of systems and how to define them or describe them. And we're also going to start off by looking at trying to find solutions through graphing. So I've already got the first line graphed. If I want to graph this one, again, lots of ways to do it. I could make a table and pick some x and y values. The thing is here, since that's 0, we only have x and y terms. I know this line goes through the origin. So we can start using some of our facts from before. So I could just solve this for y, add y over here, and then divide both sides by 4, and x equals y, and we could just, we'll call that line 2. And again, our y-intercept is 0 because there's no other numbers there. And what is our slope here? 1. So that means up 1 over 1, up 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1. So if I was to graph the system, it would look like that. Furthermore, we see that the lines actually intercept right here at the point 3,3. That is the solution to this system. So straight lines can never curve or double back and cross again, so you're going to get one solution typically. I say typically because I have a couple of examples here that are different. And that one solution will be where they intersect, because a solution means it has to make both equations true. So, for example, this point right here, that's true on this line, but it's not on this line, so it doesn't satisfy both equations. So the way you can test a solution, in this case, we're assuming 3,3 is a solution. Let's verify that, because maybe I drew the graph a little bit wrong and it looks like a solution, but it isn't. The way to verify a solution in a system is just plug it into each equation separately and see if it makes them both true. So x is 3 and y is 3 here would be 2 times 3 plus 3 times 3 equals 15. 6 plus 9 equals 15. That's true. Okay, but we don't know if it's a solution until we check it in the other one. So 4 times 3 minus 4 times 3. Okay, we can see that this works. 12 minus 12 is 0. So that's true. So since this point made them both true, that's the one and only solution, because again, lines can only cross once. Okay, let's look at a couple of cases that can occur. They're not very common. This right here is a typical case. That's generally what you're going to get. First case. All right. Here's a case where I have two lines that are parallel. So what does that mean? Like railroad tracks, they're never going to cross. If they never cross, then they can never share a point in common. So that means we're going to have no solution here at all. Let's go back up here. I had one solution where they crossed. Here, they're never going to cross. You can never find one point that makes both of these true. So here we're going to have no solutions. Now, let me look at the next case, and then we'll go back and look at all three real quick and compare some things. All right, let's look at this one. I've already plotted line 1. Here's line 2, so let me go ahead and plot that. And what I'm going to do here is I'm going to solve for y. That's usually the easiest way, but you can graph it any way you want. All right, if I want to solve for y here, let me get rid of the 4x. So let me do that over here. So I'd have minus 8y equals minus 4x plus 8. Now I'm going to divide through, hold on a minute, I got something goofed up here. I need an example that's going to work. That's not going to work. That was from another problem. Hold on a minute, let's do it this way. Okay, let's try that. So, move the 8x over here. So I'm going to subtract 8x from both sides. Still have the 4. And then finally I want to divide everything by minus 4. And what I wind up with is y equals, and this becomes 2. And this becomes a minus 1. So this equation is the same as this. But what is that? It's actually the same equation, just was written differently. when I graph this system, since that's the same line, it's just going to go right over the top of this one. So my line 2 is here, and it's actually the same line. So how many solutions do I have here? Well, both lines touch or overlap for the entire length of each one. So I have infinite solutions here. So these are your three cases. Now, without even graphing, you can look at the equations and tell immediately which system you're going to be in. It all starts with the slope. Okay, here I had slopes that were different. Here I had a slope of 1, here I had a slope of minus 2/3. But when slopes are different, that means lines aren't parallel. That means they're going to have to cross at some point. Okay, so the first thing you do, look at the slopes. If the slopes are different, you're done. You have one solution. What if the slopes are the same? That means they're parallel, but are they parallel separate, or are they parallel through the same point? Or, in other words, the same line? Well, again, start with slope. Here the slopes are the same. If the slopes are the same, look at the intercept point. If the intercept points are different, that means they're parallel, but they go through different points. That would be no solution. If the slopes are the same and the intercept points are the same, that means it's the same line, infinite solutions. So that's how you can look at a system and pretty much know immediately what you've got, even without graphing. All right, so terminology, it's here. When you're describing systems, you describe the solutions and or the lines themselves. If you're looking at the solutions, you have two terms, consistent or inconsistent. A consistent system has one or more, but really by more what you mean is one or infinite solutions. An inconsistent system has no solutions. Now, if you want to describe it by lines, an independent system has separate lines. So it has two separate, distinct lines. They're independent of each other. A dependent system has one line. It's actually the same line. It's two, but the same line. So it's as if it has one line. The lines depend on each other. So if we go back up here and we want to describe these systems, one solution, so consistent. Two separate lines, independent. So this is a consistent, independent system. How about this one? No solutions, inconsistent. Two separate lines, so independent. So this is an inconsistent, independent system. And then finally this system, infinite solutions, so it's consistent. It has one or more solutions. And how many lines? We have one line, so it's dependent. So this would be a consistent dependent system. So that's how you describe systems using these descriptors. Okay, one more thing I want to look at here. So on the previous page, the very first system we did, we were able to draw the graph accurately, and we could kind of see that it looked like it crossed at 3,3, and we even verified it, and it did. So that's fine. And That's the first technique in solving system. It's called the graphing technique, but it's really a poor technique. Number one, you got to be extremely accurate when you draw your graphs. And then number two, we're going to see that right now in this example, you got to cross on a grid line or you're estimating and you'll never get the exact solution. So let's see that here. So first thing I want to do is graph this. I can do a lot of things here. I could solve for y. Let's call this one line 1. I could go ahead and use this table idea and assign some x values and see what I get. Why don't I do it that way? Here I'll let x equals 0. And if x is 0, y is 6. And here I'll let y equals 0. If y is 0, x has to be 4. So again, remember that technique. When you don't go through the origin, you can find the intercept points quickly, and that's a fast way to graph. So at x equals 0, y equals 6. At x equals 4, y equals 0. So I've got something like this. You really need a ruler for this stuff. Okay, there's L1. Okay, unfortunately, L2 goes through the origin. I mean, that's good. I don't know where it is yet, but I know it goes through there. So I can't really use intercept points because that is the x and the y intercept points. I need another point. Okay. Again, I could solve for y and do that. I think I'll go ahead and do that because this looks pretty nice. If I add x to both sides, and then if I divide both sides by 5, so these equations are all the same. So I'll use this one now for L1. So again, my y-intercept is 0. My slope is I go up 1 over 5. So up 1 over 5, and so on. So this is a real shallow graph, linear graph that looks like that. I think you can see the problem here. That's my solution. I have no clue what that is. I would be guessing. But let's make a guess and maybe we'll get lucky, right? So that looks about halfway. So 2, that's, okay, 2, 4, so that's 3. So about halfway between 3 and 4. Let's say 3.5. 3 1/2, and let's say that looks higher up. Maybe if that's 1, let's say that's like 3/4. We're just going to guess. Let's see if we can verify that. So to make it easier for calculation, let's call that 6 7/2, and that's 3/4. All right, let's see if it works. So let's plug that point into the first equation. 3 times 7/2 plus 2 times 3/4 equals 12. So 21/2, 6/4. So if I multiply top and bottom here by 2, that becomes 4 over 42. So if I add this fraction up, 42 plus 6, that's 48 over 4. Okay, that's true. 4 goes in 48 12 times. So far it's working. Let's check it in the second equation. And I can go ahead and use this one if I want, since they're all the same. Y equals 3/4. And 1/5 times x. So 3/4 equals 7/10? No, that's not true. All right, so that means this is not a solution. We didn't guess well. As it turns out, this solution here, I've got it written down. This is the actual solution. If I plug that in for x and y here, and then here, we'll get true in both cases. That's the solution. There's no way we could have come up with that just by graphing, no matter how accurate we were. So next time, we're going to look at two techniques on how to get the exact solution for systems without doing graphing.